Chapter 7, Spillways and Energy Dissipators. 7.1 Spillway, Definition, Purpose, Types, Design Specifics, OG Shape, Cavitation and Prevention Measures. 7.1.1 Spillway. Whatever the type of dam, it is necessary to provide a safe passage for the flood water downstream to avoid the danger of the dam being overtopped. The part of the dam which discharges the flood to the D/S side is called the spillway. Requirements of the spillway: it should be designed to pass only the safe discharge downstream in the case of the maximum flood flow. It must be hydraulically, less flow separation, smooth flow at entrance, and structurally, stable and strong for different possible loading conditions, efficiently designed. As the flow velocity is very high through the passage of the spillway, its surface should have sufficient erosion and cavitation resistance capacity. There should be provision of appropriate dissipation of high kinetic energy possessed by flow at the D/S, otherwise, there will be severe bed erosion. Spillway of Adhikala HP. Function of spillway: dispose of surplus water, keeping the water level not to rise above the predefined water level for the reservoir or head pond. Spillways must have adequate capacity to dispose of entire surplus water at the time of the arrival of the worst design flood. 139. Types of spillway based on the control mechanism. Controlled spillway. A controlled spillway has mechanical structures or gates to regulate the rate of flow. This design allows nearly the full height of the dam to be used for water storage year-round, and floodwaters can be released as required by opening one or more gates. Uncontrolled spillway. An uncontrolled spillway, in contrast, does not have gates. When the water rises above the lip or crest of the spillway, it begins to be released from the reservoir. The discharge rate is controlled only by the water depth above the reservoir's spillway. Storage volume in the reservoir above the spillway crest can only be used for the temporary storage of floodwater. It cannot be used as water supply storage because it is normally empty. Based on purpose: main spillway. Main spillway is designed for the safe passage of the designed maximum flood. Auxiliary spillway. The auxiliary spillway is the supplementary spillway to the main spillway. It is favorable to provide the auxiliary spillway when there is natural saddle. Emergency spillway. The emergencies arise when incoming discharge exceeds the maximum design flood or when the gate of the spillway malfunctions during flood. To avoid serious accident during such conditions, an emergency spillway is provided. Based on prominent feature: free fall spillway. A free fall spillway is one in which flow drops freely from the crest. This type of structure is not adaptable for high drops on unstable foundations because of the large impact of the forces downstream. So, a pool of water can be created downstream to dissipate energy. 140. OG spillway. In this type of spillway, the upper curve of the spillway ordinarily conforms closely to the profile of the lower nap falling from the sharp-crested weir. It is generally used in high solid gravity dam. If the discharge over the spillway is more, then the flood nap may separate from the body profiles, creating cavitation, which is undesirable in dam. The profile of OG spillway is shown below. YC equals 0.175H, XC equals 0.282H or equals 0.5H or equals 0.2H. Discharge through the OG shape spillway, Q equals CLH. HO equals HD plus HA, where Q discharge over the spillway, CD coefficient of discharge, low effective length, heat effective height. 141. HD actual head at the spillway, HO head due to the velocity of approach. Side channel spillway. A side channel spillway is one whose control weir is placed alongside, approximately parallel to spillway discharge channel. Flow over the crest falls into a narrow trough opposite the weir, turns approximately 90 AMD, continues into the main channel. Flow from the side channel is directed into the open channel or a closed conduit, finally disposing surplus water downstream. Chute spillway. 142. A chute spillway is a common and basic design which transfers excess water from behind the dam down a smooth decline into the river below. These are usually designed following an OG curve. Most often, they are lined on the bottom and sides with concrete to protect the dam and topography. Siphon spillway. A siphon makes use of the difference in the height between the intake and the outlet to create a pressure difference needed to remove excess water. Siphons, however, require priming or the removal of air in the bend for them to function, and most siphon spillways are designed with a system that makes use of water to remove the air and automatically prime the siphon. Morning Glory Spillway. In this spillway, water drops through a vertical shaft and flow downstream river channel through a horizontal conduit. Top level of the vertical shaft is kept at normal water level. Excess water enters through the flared vertical shaft and discharges downstream. 143. Cavitation. Cavitation is a phenomenon in which rapid changes of pressure in a liquid lead to the formation of small vapor-filled cavities, in places where the pressure is relatively low. When subjected to higher pressure, these cavities, called bubbles or voids, collapse and can generate shock wave that is strong very close to the bubble, but rapidly weakens as it propagates away from the bubble. Spillways for medium and high head dams may be exposed to high velocity flows and the associated destructive phenomenon of cavitation. Cavitation may occur at rough spots in the surface of the chute or tunnel, at local discontinuities in the finished surface such as construction joints, and at locations along critical flow profiles having significant deviations from design specifications. Preventive measures of cavitation in spillway. The prevention of the cavitation phenomenon can be effected by eliminating opportunities for flow separation, by limiting flow velocities to non-cavitation levels, or by maintaining sufficiently high operating pressures. Elimination of any opportunity for flow separation, including the construction of very smooth surfaces which have negligible surface roughness and which are devoid of holes or grooves, will eliminate the occurrence of cavitation. Flow surfaces must not exhibit significant deflection so that the high-velocity jet will remain positively supported at all times, and construction joints must be perfectly level so that no protrusion into nor away from the flow is experienced. 7.2 Method of energy dissipation below the dam structure. Types of energy dissipators: ski jump, flip bucket, stilling basin, and their necessity. Natural type of energy dissipator, role of tail water depth. As stated earlier, the water falling through the spillway has high velocity. This velocity may cause serious damage downstream. Hence, the high energy of water should be dissipated to reduce the damage to the structure downstream. The energy dissipation takes place by two methods, i.e. hydraulic jump formation and hydraulic diffusion. 144. 7.2.1 Types of energy dissipators. Energy dissipation below the overflow sections of river diversion structures shall be achieved through one of the following structures. Hydraulic jump type stilling basins. This structure dissipates energy through formation of controlled hydraulic jump within the confines of the basin over the entire range of flow conditions under which basin is expected to operate. The design of this basin shall depend upon the type of jump expected, i.e. Froude number of incoming flow. Fr equals Vgy, where V equals velocity of flow, Y equals depth perpendicular to stilling basin. The stilling basin may be horizontal apron type or sloping apron type. The stilling basin shall also consist of chute blocks, baffle blocks, or end sills to make it economical. Roller buckets. Roller buckets shall be used below the overflow sections to dissipate energy in conditions where the tail water depth is much in excess of sequent depth. Energy dissipation shall be achieved through two complementary elliptical rollers, a surface roller formed over the bucket and a ground roller formed downstream of the bucket. Roller buckets may be solid roller type or slotted roller type. Deflector or flip buckets. The flip bucket shall be used to dissipate energy in situations where the tail water depth is insufficient for the formation of the hydraulic jump. It consists of an upturned solid bucket that throws away the incoming flow to a considerable distance downstream of the overflow section as a freely discharging upturned jet which falls. 145. Into the river channel directly, thus avoiding excessive scour immediately downstream. For a particular site, the type of energy dissipator and its arrangement shall be decided based on the relationship between the heights of the hydraulic jump versus tail water depth. The graph between specific discharge and tailwater is called tailwater curve TWC, and that between specific discharge and jump height is called jump height curve or Y2 curve. For any situation, there are 5 cases. A. TWC coincides with Y2 curve. Hydraulic jump will form at the toe of spillway at all flow rates. In this situation, a horizontal apron stilling basin shall be used for energy dissipation. B. TWC lies above Y2 curve. In this case, the jump formed will be drowned by tailwater. This problem can be overcome by constructing a sloping apron over the river bed level or by providing a roller bucket type energy dissipator. C. TWC lies below Y2 curve. Tailwater depth will be insufficient for the formation of a hydraulic jump. In this case, energy dissipation shall be achieved by lowering the apron level of stilling basin, providing horizontal apron with baffles and sills at the riverbed using a deflector bucket, providing subsidiary dam downstream. D. TWC lies above Y2 curve for low discharge and below Y2 curve for higher discharge. In this condition, a bucket-type energy dissipator that acts as roller bucket for low discharge and as a deflector bucket at higher discharge may be provided on sound rock conditions in river channel. 146. E. TWC lies below Y2 curve for low discharge and above Y2 curve for higher discharge. In such case, enough tailwater depth shall be artificially created to form a jump on the apron at low discharges by constructing horizontal apron stilling basin with low secondary dam. 7.3 Design of stilling basin. Standard stilling basins. 7.3.1 USBR stilling basin type I. This is the simplest form of the stilling basin. It consists of apron and end sill only. This stilling basin is used where incoming fruit number is less than 1.7. USBR type I stilling basin. USBR type 2 stilling basin. 7.3.2 USBR stilling basin type 2. This type of basin is recommended for use on large structures such as dams and spillways where incoming fruit number is greater than 4.5. USBR stilling basin type 3. This stilling basin is used when incoming fruit number is greater than 4.5 and velocity greater than 20 meters per second. 147. USBR stilling basin type 4. This stilling basin is used when incoming fruit number lies between 2.5 to 4.5 and velocity less than 20 meters per second. 7.3.3 Design steps of stilling basin. 148. Find the width of stilling basin, B, if head over the crest, H, is known or vice versa using following formula, Q equals 23C2GBH. Calculate pre-jump depth Y1 by applying Bernoulli's equation between 0, at crest, and 1, at the start of hydraulic jump, P gamma plus V2G plus, Z plus H, equals P gamma plus V2G plus, Z plus Y. Where P0 equals P1 equals atmospheric pressure equals 0, V0 equals approach velocity, neglected being small, Z1 equals 0, hence, Z plus H, equals but, Y equals thus, Z plus H, equals calculate the sequent depth, Y equals Y21 plus 8 FR minus 1. Here, FR equals calculate the normal water depth Y0 using Manning's equation, Q equals 1 eta by RS. Find critical depth. Y equals QG. If YC Y0, then hydraulic jump is formed. Select the suitable type of stilling basin. 149.